It's a great pleasure to have our own near Sloane. It's a tradition that every year, academic year, the first talk is by Neil Sloane. It has been for quite a few years. I don't remember exactly how. Unlike the usual request that you're supposed to mute yourself by request of the speaker, by Neil invites you to stay unmuted. And you decide whether you have a dog or a baby or somebody. So if there's no distracting noise, please stay muted. Go ahead, Neil.
And that reminds me, I should turn off my phone.
Oh, yeah, good idea.
All right. Okay, shall I go ahead?
Go ahead.
Okay, so I'm going to talk about cutting a pancake with various shaped knives. And okay, the arrows now work. Okay, the outline of the talk is here. I'm going to talk about long-legged letters and the graph and various examples, some nice results, lots of examples, some unsolved problems at the end. So the basic problem is you've got a knife, which might be a straight line or it might be a circular cookie cutter, and you've got an infinite pancake on the plane, and you put down your knife and you make a cut, and then you make another cut, and you want to make as many pieces as you can. They don't have to be the same size. It's just the number of pieces that you want to maximize. And you might even have a V-shaped knife, like an example in concrete mathematics. And generalizing that, you might even have a woo-shaped knife. In case you're not familiar with a woo, it's like a V with 3 arms. And if you look it up with one of those shape recognizing programs, it'll tell you that it's one of the symbols in the Canadian Aboriginal set of symbols, on the Unicode symbols. Anyway, that's a woo. But I think of it mostly as a V with 3 arms. There are also X's, long-legged letters, etc. Okay, the simplest case is where you just have an ordinary knife and you make a cut. Your knife actually is a line, which means it's infinitely long. If you make 1 cut in the pancake, you get 2 pieces, obviously. 2 cuts, you get 4 pieces. 3 cuts, you might think you get 8, but you only get 7. But what you do, and the general philosophy is, when you make a cut, you try to cut all the previous cuts, intersect all the previous lines, and then it goes up from 1 to 2, 2 to 4, you add 2, 2, 4, 7, 11, 16. It goes up by 1. It's a quadratic. The amount you add grows up by 1 each time. The differences grow by 1. So the sequence is 1, 2, 4, 7. If you have no cuts, then you have 1 pancake. So the 0th term is 1. The formula, these are triangular numbers plus 1, and it's sequence, one of the oldest sequences in the OEIS. It's sequence 1, 2, 4. And it's mentioned in page 7 of Concrete Mathematics. And in general, we ask, if you've got a shape, what's the value of A sub S of n, the maximum number of regions you can get by drawing n copies of S. And the individual copies of S, they don't all have to be the same size. Some circles can be bigger than others. If it's a circle, you can turn over the shape, you can rotate it, stretch it, and so on, just as long as it looks like an S. And then the question is, how many regions can you make? And for extra credit, something we know very little about, how many different solutions are there? There are a couple of cases where we know the answer, but usually we don't. Now, I should say that although this may sound like recreational mathematics, it originated in the first chapter of a book by some of the greatest names in discrete mathematics, Graham, Knuth, and Potashnik. And, furthermore, there are some new and surprising theorems, difficult unsolved problems, and there may even be applications. I can't help think that some gerrymandering rule might appreciate these constructions. Anyway, and finally, one of the nice things is it's great to be working on a problem that I can explain to my neighbors, to anyone. All right, so I already showed you the pancake cutting problem when the knife is a simple straight line. What if it's a circle, a circular cookie cutter? So if you make one cut, you get two pieces, the outside and the inside. We always count the infinite part as well. If you make two cuts with a circle, you get 4 pieces. 3 cuts, you can see here, you get 8 pieces. And this, of course, is the famous Venn diagram with 3 sets. If you have 4 circles, you can only get 14 pieces. And the formula is n squared minus n plus 2. And that'll be a simple example of the method later. If it's a square, you put down a square cookie cutter and you get 2 pieces and so on. And again, the rule is you maximize the number of intersections between existing. Sorry, is there a question? I just say. Sorry? No, all right, I'll continue. So the rule generally is to make as many intersections with the previous cuts as you can. So you put down one square, and then your second square overlaps it a lot, and you pick up 8 extra little triangles, and the inside and the outside, and you get 10 regions with 2 squares, and so on. And the formula is 4n squared minus 4n plus 2. And it's sequence A, another old sequence A, 069894. Another companion to that, this works for convex quadrilaterals as well as squares. You don't gain anything by using a different shaped quadrilateral. You may as well use it. You should use a square. If you have a concave quadrilateral, what if you poke in one side of the square? Then again, the sequence is it's roughly 8n squared. And for all of these, the formula so far has been a quadratic. And you might think we're only ever going to get quadratics. But in fact, a simple example is the Venn diagram question. If you have a Venn diagram for 3 sets, is a way of drawing a picture in the plane where you can distinguish the points that have property A and don't have property B, or have properties A and B, or in the middle properties A, B, and C. You want to have 2 to the n regions where all the possibilities occur. And with n equals 3, you can do it with circles. With n equals 4, you can't. 4 circles, I showed you the maximum number of regions you can get with 4 circles is 14. We need 16 regions for 4 different kinds of sets. And you can do it with 3 circles and an ellipse, as John Wilde pointed out to me the other day. But the construction which generalizes is the following. This is from a paper of Branko-Grunbaum in 1975. And he uses, I forget what he calls them. I call them sausages. They're simple Jordan curves, like sausages. A circle is a Jordan curve, of course. And we take 3 circles. For the 4th circle, it's drawn in red here, and it's a sausage shape, and it goes around, and it meets all of the previous regions. And then for 5 circles, it's the green curve, and it goes around and around, and you do it in such a way that it meets all of the previous 16 regions at least once, and so on. There's a 6th dotted line here, but obviously this generalizes. And so with n sausage shapes, you can get 2 to the n regions. In fact, you can get a lot more than that. If you have just 2 sausages here, I've drawn them as snakes. You can see they interleave each other. So with 2 sausages, you can make as many interleavings as you want. So a simple Jordan curve of 2 is unbounded. You can make it as large as you want. And in fact, if you're willing to have a twisted sausage, like this picture here, even with 1 sausage twisted, you can get arbitrarily many regions. So one is unbounded. So in order to avoid all these complications, I'm going to assume that our shape S is a connected planar graph that's only got straight line edges. It's made from polygonal pieces. I mean, straight line segments only. Some of them may be infinite, but it must be connected. So that's going to be the rule from now on. And then this project really started when I was looking through concrete mathematics back in May, and I noticed in the first chapter they do 3 examples of this problem. They look at the straight line, the classic pancake problem. Then they do the case: what if your line is bent? If your knife is bent, so it looks like a V, but with very long arms. They call this a bent line. And then they do a doubly bent line that they call a zigzag. It looks like this. And the definition is it's 2 parallel rays joined by a segment. And they work out what the answers. Well, they don't do the Z very well. That's an exercise with, I think, a fairly inadequate solution at the back of the book on page 499. But still, it's enough to do it. So I was thinking how you could generalize these. So think of these as letters. This V-shaped, I think of as a V with long legs. This is a long-legged V. This is a long-legged Z. And I looked at some others. And so here, I actually was most interested in the long-legged A. I thought that would be really interesting. What if you're a cookie cutter? What if this is your knife? It's a V with a crossbar, and the crossbar doesn't have to be horizontal. It's just a crossbar somewhere. And then, of course, a straight knife is a long-legged I. And there's a long-legged V. Here's a long-legged X, and here's a long-legged Z. And those are the long-legged letters. And I called them long-legged letters because I keep thinking of a poem a poem of Yeats, which, when you've heard it, tends to stick in your mind. It's called Long-Legged Fly, and there are 3 verses. The first verse is that civilization may not sink, its great battle lost. Quiet the dog, tether the pony to a distant post. Our master Caesar is in the tent where the maps are spread, his eyes fixed upon nothing, a hand under his head, like a long-legged fly upon the stream, his mind upon silence. And I often think of this because where I live, every day there are leaf blowers and other things going on, sirens and so on. And last night when I was putting the slides together, I looked at the back page of the back cover of Concrete Mathematics. And here are Knuth, Graham, and Potashnik with their hands under their chins. I don't know if you remember, this is from the 2nd edition. In the 1st edition of Concrete Mathematics, they've reversed this negative. So Rn is on the left, and they all seem to be left-handed. Because I think if you're right-handed, and you put your hand under your chin, you put your left hand under your chin, right? So, and they corrected it, I think, for that reason. So, anyway.
Did Knuth and Graham know about this poem by Yeats?
I'm sorry, what did you say?
Did
Knuth? I don't know.
Did they know about the poem? Was the picture inspired by this poem by Yeats?
No, I doubt it. I think it's just a natural thing. When you want to take a picture of three mathematicians, it's a very natural thing to do.
Yeah, it's good.
So I'm going to show the solution to a whole bunch of problems. And the solution is always using graph theory, planar graphs, elementary combinatorics. And so we're given a shape. I'll show you how I build up the graph. You take your shape, one copy of the shape. It's a graph. It might be a V or a woo, or a thing called a 3-chain. A 3-chain is like a ninja nunchuck thing. It's got 2 long arms joined by a finite segment, and it has swivels. It has points in 2 places, so you can move the arms around. This is a 4 chain. It's got 4 segments, 4 line segments. The end 2 are always infinite, and the middle 2 are finite. This one was actually suggested by my co-author, David Cutler, who also worked out the number of regions for this. Anyway, so we're going to make a graph. We're going to start off by putting down 1 copy of the shape. And it's a graph. The graph for 1 copy of S. It has nodes, which are colored red. I will call them the base nodes because they come with the shape. You can't do anything about them. You're stuck with them. And then there are edges coming out of the base nodes, and I call them arms. So these 2 have a special meaning, base nodes and arms. Now, suppose another thing is, of course, this 3 chain, you can move this arm around over there, and you get something that looks like this. I think of this as a picnic table. It's got a top with 2 legs, right? And you've picked up 1 intersection, 1 crossing, which is marked in black. If you have a 4 chain, you can get 3 extra intersections, self-intersections. And if you have a 5 chain, you can pick up 6. In general, the number of self-intersections you can get is, for a K chain is K minus 1 choose 2. And I define that to be sigma. Sigma, there are 2 parameters for the shape that are very important. One is the number of self-intersections, the maximum number of self-intersections you can make. For a K chain, it's K minus 1 choose 2. For a V, it's 0. These arms don't intersect each other. They do at the base node, but that's part of the definition. That doesn't count as an intersection. So we have 2 kinds of intersections. We have crossing nodes where the arms cross, and we have the base nodes. Now suppose we have 2 copies of S. Here are 2 copies of a WU. They've got 2 base nodes, and the arms intersect. Well, they could intersect not at all if the arms pointed in different directions. The maximum number of intersections you can get is 9 if all 3 arms cross all 3 other arms. And I call that number chi. Chi of S is the maximum number of crossings you can get with 2 copies of S. So we've got 2 parameters, sigma of S and chi of S. And in many simple cases, it's enough, if you know them, to work out the answer to the number of regions. Anyway, continuing about the planar graph, one thing you can do, since we're placing these, I'm going to insist that you never put an arm through somebody else's base node. Because if you did, you could make a microscopic adjustment to this arm and pick up some extra regions. So I decree that no arm goes through a different base node. I also decree that no triple intersections for the same reason. Okay, and then I use V for vertices or nodes, E for edges. Some edges are infinite, some edges are finite, E infinity and EF, and they're the edges. The graph is what you get by putting down all the copies, making all the cuts, and stepping back and looking at it as a graph. And every time that, I should have said, every time you get a crossing, you get edges. The edges are what happens when the arms cut other arms. They're the edges in the graph. And R is the number of regions. There are infinite regions and finite regions. And then the master, Euler, tells us 2 things. If the graph is infinite, then the Euler characteristic of the plane is 1, and we get edges minus V plus 1 is equal to the number of regions. On the other hand, if you keep your graph finite, and you like a polyhedron, and promise not to have any infinite edges, then Euler says, all right, you can have 1 more region. And the formula this is for polyhedra, polygons, and similar things. R is equal to E minus V plus 2. And I thought I'd be able to find a proof of the Euler characteristic of the plane in one of the many books on geometry, but I haven't succeeded. But one of the correspondence to the Math Fun list, Gareth McCann provided a proof that the Euler characteristic of the plane is 1, and it's here for anyone who doesn't believe it. And on the other hand, for the Euler characteristic of a finite region, for instance, the surface of a sphere, it's 2. And there's a book, there are many books. Any book on graph theory has a proof for a finite graph. E minus v plus 2 is equal to the number of cells, the number of regions in the graph. And there are many proofs of it. And there's a book, in fact, by Lakatos called Proofs and Refutations, which gives about a dozen proofs in the form of a Socratic dialogue between a master and many disciples. Different proofs because there are many ways to state this and many objections. Do you allow a hole in the graph and in the surface of the polyhedron and so on? And after you've read that, you never want to see another proof of the Euler formula. But it's in every book. It's in Coxeter, it's in all the books on graph theory and so on. The +2 version. So that gives you an equation that relates the parameters. What makes everything work is that there's a second equation, which is obtained by counting all the times an edge and a vertex meet. You count edge-vertex intersections, and you count them in 2 ways. Standard combinatorial idea. So I'm going to get an equation. On the one side, I'm going to count the edges one way. On the other side of the equation, I count them another way. So first of all, taking the point of view of the vertices first, every base node has a given number of edges. This is a V, and it has 2 edges coming out of it. The degree of this base node is 2. The degree of the base nodes in general, I call it d sub v, degree of a base node vertex. And then there are also crossing nodes. Every time 2 arms cross, you get a crossing node, and my rules have set it up so it's always 4. The degree of a crossing node is 4. So on the left-hand side, we've got the sum of the degrees of all the base nodes. We've got 4 times the number of crossing nodes, and that is almost counted every edge twice, because every edge has 2 endpoints, and it's counted twice, except for the infinite arms. We don't have any vertices at infinity in this game. So infinite arms and infinite edges only get counted once when I've done that. So I have to add in the number of infinite edges to get the total to come out to be twice the total number of edges. So on the left-hand side, we counted every edge twice. On the right-hand side, well, we've got infinite edges, EF finite edges, and they're all counted twice. So we have this identity. And this, let me rearrange it to extract E sub f, the finite number of edges in terms of the other things. And now we take Euler's formula. This is assuming we've got an infinite graph. We take Euler's formula, regions equals edges minus vertices plus 1. Plug in EF. This contributes twice the number of crossings, but we're subtracting VC crossing number once. So the basic equation says for this graph, the number of regions is the number of crossings plus some other stuff. But the thing about the other stuff is that you have no control over it. It comes with the problem. You're given what the shape is, and the shape determines the base nodes, their degrees, and the number of them depends on n, and the number of infinite edges. All of that you can't change. All you can change are the crossing numbers. So the moral of this is, if you want to maximize the number of regions, which is what the game is, you maximize the number of crossings. It's if and only if. There's a similar thing if it's a finite graph. You change the 1 to a 2 and you drop the infinity. Now, the final ingredient is that we have an upper bound on the number of crossings. The way we've defined things, the number of crossings is at most, for every shape, you may pick up self-crossings. So you get n times the number of sigma of s, the number of self-crossings, plus for every pair of s's, you pick up the number of intersections, which is chi of s. So this is a crude upper bound, n times sigma of s plus n choose 2 times chi of s. And the nice, surprising thing is, this works in many of you get equality. If you're clever enough to figure out where to put, you have to do some figuring out to make sure you can attain it, but usually you can. And so these two equations are the basic equations for the whole game. So let me do a couple of examples. The straight line, the pancake graph. So S is a straight line. It has no vertices and it has one edge. But I'm going to assume that we've put it together so that edges cross. So every edge, in fact, will cross some other edge, so it'll have two infinite parts. So the number of infinite edges is twice the number of edges. I'm assuming that n is bigger than or equal to 2, and we're not doing anything stupid. We're going to make sure that every edge cuts one other, every knife cut intersects at least one other knife cut. So E infinity is 2n. A cut can intersect itself once. So that the cutting number for two lines is 1. There are no self-intersections. So the number of crossings is at most that. So the number of regions is at most n choose 2 plus n plus 1. And you can achieve it just by making every line cross all the earlier lines. So that gives a proof of the classical formula for cutting a pancake. And I must say, I looked online at various to see proofs of that, and there are a lot of proofs, and they're mostly bogus. But anyway, it's simple enough to prove with our approach.
So did Knuth and Graham and Potashnik have a proof?
Yes, they do. In fact, they start off with that, and they do it by induction, showing that when you I'm not quite sure exactly. I didn't read it very carefully, but it's there. There's on page 9 or something of the book, in part of the text, and they do the Z as an exercise, and they do the V also as part of the text. All right. Now the next simplest thing, shape after a line, is a ray. A ray, by definition, is a distinguished point with an infinite half line going out of it. And in order to emphasize the difference, I call that a hat pin, because if you come across a photograph of your grandmother wearing a hat, she probably has a pin through it. There's a ruby or something at one end and a very long pin. You have to be, in order to use that, of course, you have to be female, you have to live 100 years ago, and you have to have hair. All right, so if you have n hat pins, the number of base nodes is n. You get one for each head, each red dot. The degree is 1. You've got infinitely many edges. You've got n infinite edges, so E sub infinity is n. The crossing number is 1, and the formula gives the right answer, which is n choose 2 plus 1. And here's an example. This is a hat pin graph with 4 hat pins. And you can see basically it looks like straight lines. It's basically the same as the pancake argument. But it's useful. I need in a minute, I'll need both the pancake graph and the hat pin graph to build up other graphs from them. All right, the next example is a K-armed V. A 3-armed V, remember, was a woo, but I'm going to do a K-armed V, where K is bigger than or equal to 1. K-armed V, or a K-armed VU for that matter. And so here's an example of a 3-armed V. This is actually a true woo. So you do the arithmetic, and you say, all right, if we've got K-armed V's, the degree is K, the self-crossing number is 0, the crossing number for 2 of them is K squared, where the K-arms cross k more arms, the most you can get of intersections is k squared. And you get an upper bound on crossing numbers, and that gives you an upper bound on the number of regions. And if you could achieve it, then that's the answer to what happens with a k-armed V. And in fact, yes, you can achieve it by the following construction. You take, in this case, a V is a bit like a hat pin. It's a generalized hat pin. It's got k arms instead of one. So you take your hat pin graph, and you take a lot of long, skinny V's, and you just replace the knives, the hat pins, by the V's, and you get the right number of intersections, and you get a proof that it works. And I should say that I talked about this at the Research Experience for Seminar, Research REU for undergraduates at Rutgers in June, and I mentioned a number of unsolved problems. The Heraclitus transform, which, Daron, you may remember I talked about once at dinner.
Yeah.
But I mentioned the woo question, because I thought the students would be amused by learning about a symbol they hadn't seen before called a woo. and what after I described the problem and shown this graph, I didn't show this graph because this gives away the whole sequence. What I showed was a way of drawing three woos, which is much more complicated, where you put down a woo with its widely spaced arms and put another woo on top of it and try to juggle them around to get the maximum number of regions. And a student, Edward Xiong, said, really, he thought about it for a moment in the audience, and he raised his hand and he said, really, all you have to do is get as many intersections as possible. And that's actually true, but it does, in order to make it rigorous, it does require proof. But yes, and later the next day, he sent me an email with the formula. What they thought was, they said, this is almost certainly the formula for the number. It's this formula with k equals 3. In fact, he said that they came up with it after my talk. They got together in the afternoon and came up with this formula. And the next day, David Cutler sent me an email saying that he'd been considering the thing in the next slide, which is the k-chains. He said, look at k-chains, and you can have this many self-intersections. And he had worked out what he claimed was the number of regions you can get. Here, you have to place not only the k-chains on top of each other, you also have to modify, you have the freedom to get self-intersections by moving the arms around. So his formula was this: a quadratic in n for each k. Don't think he had a construction, but he had the formula. But there is a simple construction. You just use either the pancake graph, if k is odd. So if k is odd, the 3-chain looks like this. It looks like a picnic table. It's got 3 arms, it's got 2 base nodes, and it comes in from the left and goes out on the right. And the idea is to do the same thing that we did here. You take either a pancake graph or a hat pin graph and replace the cuts here by the k-chains made into long, skinny k-chains. And if k is odd, you use the pancake graph because they come in at one side and go out at the other side. And if k is even, so that it looks like this, you use a pancake, a hat pin graph. And you can guess that. So, and they sent me, it wasn't quite clear to me if they had proved this or not. They sent me emails saying, it looks like it, we think the following is a proof. Long and a bit difficult to read. And it's the sort of thing when you look at it and you say, I think I'll try and prove it for myself. And I did. And oh yeah, here's an example of taking.
But they had the upper bound, right?
Yes. Yeah. No, but you need the counting formula, the edge vertex intersection formula to get the upper bound.
Yeah.
And it's not clear to me that they had that. Maybe they're in the audience and they can correct me. I told them, invited them to the talk. So here's an example of taking 3 cuts and three chains and replacing the cuts by. So Pancake graph gives you that. All right. So here's a table. This is where it gets interesting. Here's a table of the values. On the left, this is how many regions you can get with a K-legged V, or K-armed V. I don't know if a V has arms or legs, but whatever it has, let's say it has arms. If this is the number of regions you can get with a K-armed V, and you have n of them. And if you have if you have a one-armed V is a hat pin. It's got a distinguished node and a ray coming out of it. So a one-armed V is a hat pin, and you get the hat pin sequence. A one-armed chain, a one chain is an edge, is an infinite edge. And so a knife cut, an infinite knife cut. So you get the pancake sequence. And these two sequences are essentially the same, except because the V has a distinguished node, it's shifted by 1 point. The number of infinite edges changes. But apart from that, they're the same. If you have a regular V, a long-legged ordinary V, and a long-legged ordinary 2-chain, they're identical. There's two lines with a base node joining them. And of course, you get the same sequence of numbers. But the surprising thing was that if you look at a 3-armed V, that's to say a woo, and you look at the 3-chain, which is the trestle table, and you look at the number of regions you get, they're the same. And this was a surprise. One, 3, 14, 34. And I will explain that in 2 slides. But first, I want to talk about the long-legged. The reason I got interested in this in the first place was the long-legged A. I wanted to see what would happen if you had a cookie cutter which was shaped like an A with a variable crossbar. So here's what I came up with drawing 2 A's. Here's one A, here's its apex, and the red line is its crossbar. And here's another A, apex and crossbar, and I've moved things around so as to get the most number of regions, which we know is also the most number of intersections. And that's the best you can do, and it has 14 regions. And the crossing, the chi of an A is 9. There are 9 intersection points between the 2 A's. Then if you do 3 A's, you can get 34 regions. So the sequence for A's began, so if you have 1 A, there are 3 regions. The triangle, between the legs, and the outside. So there are 3 regions for 1A, so it goes 3, 14, 39. And if you look at this table here, you see 3, 14, what did I say? I should have said 39, 34. Okay, the sequence goes 3, 14, 34. 3, 13, 34. They're the same. So this line is not only the maximum number of regions you can get with n trestle tables, n 3-chains, and n woos, it's also the number of regions you can get with n A's. And so here's the proof. Suppose you have an A. Here's an A. Suppose you have a graph with a lot of A's in it, and you ask each A to raise its arms above its head. You take, here's the A, you say, move that arm up there, and move that arm up there. and you get this, which is a 3-chain, a trestle table upside down. So you do that for all the A's, and it gives you a map from A's to 3 chains. So that explains why those two numbers are equal. What about the woos? Well, all right, so take a graph with a lot of A's in it. Look at a typical crossbar in the A, and one of the ends of the crossbar will be closer to the tip than the other, or if they're the same, pick one at random, it doesn't matter, and move the end of this crossbar until it's closer to the tip than it was before. And that, you can see here, that would increase the number of regions by 1. It may not increase the number of regions, but it doesn't decrease them. The other end of the crossbar, you move it away from the tip, down there, and same thing, that would increase the number of regions, or not decrease it. So after you've done that, for each crossbar, one end is close to the tip of that A, and the other is along furthest from the tip. Now you move that end to coincide with the tip, and you move the other end down between its legs and cut it free, and you get this, which is a woo. And you can reverse the process. So that proves the sketch-proof theorem. Okay, the other mystery, the other observation about this table is still unexplained. If you look at, this is the table for NK chains. It looks like this. We just saw the sequence where we have 3 chains and n of them. This main diagonal goes 1, 2, 7, 3, 4. Across the diagonal, the numbers are very nearly equal. This is very nearly symmetric, this table. The difference, in fact, because we've got a formula for this, for these numbers, the difference between the two entries, the kn entry and the nkth entry, is twice absolute value of n minus k. It's the difference in the number of infinite regions. You can't avoid it. So apart from that, this is a symmetric table, and this is a mystery. Why is that true? It's true, and I can prove it, but what's the geometry that causes it? And one possibility is one possible explanation which doesn't work is that there's a one-to-one correspondence for optimal graphs with nk chains and optimal graphs with kn chains. And that's not true, because I think this is pretty nice. You look at, let me look at the case where you're looking at 1 chains, and you've got 5 of them. 5 1 chains is 5 lines. Each 1 chain is an infinite line, a simple knife cut, infinite knife cut. And to get the maximum number of regions with 5 of them, you want to put the lines in general position. You want to make sure every pair meets and no triple meet at a point. And it turns out there are 6 ways to do that. And this is a sequence that mostly Jonathan Wild worked on. I made a video on YouTube, Numberphile, about it. There's some beautiful pictures of anyway, so sequence, it's sequence 90338. We now, other people have extended this. We now have 9 terms. It's the number of lines in general position in the plane. It's the number of ways to place n lines in general position. If you put down 1 line, there's only 1 way. 2 lines, only 1 way. But when you get up to 5 lines, there are 6 ways. And here they are. They're obviously different. And so that's the 5th term in this sequence. And we know 9 terms. Now, on the other hand, if this guess was correct, there would be 6 ways to do 1 5-chain. So a 5-chain is basically, it's a pentagram. You go there, and there. But there are only 2 ways to do it. After you've done the trestle table, the intersection point of the other 2 lines is either inside the triangle or outside. So this sequence goes 1, 1, 1, 1, 2, and that's as far as I know it. I asked Jonathan Wild if he knew any more terms, and I'm hoping he'll come up with an answer. The circle. You can do the circle in the same way, and there's a very nice construction, and the formula works, and the formula gives you n squared minus n plus 2 as the answer, and you can achieve it by drawing a circle, a red circle for construction purposes, and taking n equally spaced points around it, and taking them as the centers of your circles, and it works. So we get equality. We know the answer there. And a couple of other shapes that I solved, and the reference to our paper, if anyone is interested. It's very nearly finished. A few corrections after preparing this talk. There are several letters that I wanted to look at, like an L. If you looked at a long-legged L and allowed any angle, an L would become a V. So, but I wanted to look at L's which have 90-degree angles. So I call that a constrained L. A constrained long-legged L is a fixed point with two perpendicular rays coming out of it. It looks like that, and it's easy enough to work out what the formula is from our thing. It might not be exact, it might not be attainable, but it is, and I made a construction for it. Here's an example using 5 L's. The red dots are the base, the corner node of the L, and the construction is based on the construction for squares. I do the squares construction, but only use 2 of the sides of the square, and you get that. That's an example with 5 L's. Another example that I really liked and only solved recently was, what if you have an X and you constrain it so that the angles, the 2 lines are perpendicular. So a constrained long-legged X is a distinguished point with 2 perpendicular lines through it. And you can get a bound, and but it was very hard to find a construction. It took quite a while. And here's the construction. And I really want to show you this. These are 3 things that are still open. What if you have a constrained T? A constrained T is a line, the bar, a crossbar, and a stem. And the bound, our theorem says the upper bound of the number is 2n squared plus 1. And you can achieve it for 3 T's. Here's 3 T's. But having done that, I believe there's no way to add a 4th T. And furthermore, this is unique. So here's an example where our bound, it can't be achieved. It can't be achieved for n bigger than or equal to 4, and I don't know what the exact answer is. Another interesting example is a constrained A, where you make the horizontal, you make the crossbar horizontal, and there's a formula, I conjecture that. And another interesting case is the figure 8. Take 2 circles, they have to be equal circles, but they can be as big as you want, and the theory doesn't work because you can't. You're getting 2 circles, and you can't get as many crossings as you would like. So I have a conjecture, a weak conjecture, and there are many other examples in the paper, and I'll just show you. I worked on this, the pentagram. What if you have a pentagram? How many regions? It came up because of the 5 chain involves pentagrams. Anyway, with a pentagram, you can get, here's 1 pentagram, here are 2 pentagrams, here are 3 pentagrams, and here are 8 pentagrams. And Scott Shannon made these beautiful pictures. The red region, it's color-coded, the red regions are quadrilaterals, the tan regions are quadrilaterals, and the red regions are triangles, and the central region is whatever it is. I guess 3 times 5, it's 15. So 15 gone, and there are 77. I think my time is up. Any questions?
Yes, thank you. Fantastic. Let us mute yourself and thank Neil for a great talk. It's amazing, this elementary problem. is so sophisticated and
Yes.
really great. Yeah, I have a question. Being an expert, can you characterize those shapes that are always quadratic? Many of them are quadratic, except
Yes, yes, I think so. I think that all of the ones you get from this assumption that S is polygonal, they can't be more than quadratic because the degree of the nodes can't be more than 4, and everything is bounded. So I think they're all quadratic.
So a numerical approach would be to have a computer to draw such things in general position, count it, and have 3 data points, and to be safe, 4 or 5 data points, and fit it with a quadratic. So at least we'll be a way of deriving the formula.
Well, or getting an upper bound. You could do that with a T, and it would give you the wrong answer.
Okay.
But yes, I agree. In fact, of course, we've all done a lot of experimenting. In fact, I've filled up almost a whole 200-page notebook this summer with drawings and calculations. And,
Have a beautiful picture. Another quick question: what about planes in 3 dimensions or
yes, in fact,
hyperplane?
Let me say that David Cutler wanted to make everything much more rigorous, and I said, you save that for your sequel to this, because he's been looking at the 3 higher dimensional versions of this problem, and so I would like to encourage him if he's listening.
So then, but is it known for the simplest case where you have planes?
Yes, it's sequence A125.
And then it's cubic probably, right?
124 is cutting a pancake. A125 is cutting a cake, with a real cake with a hyperplane. How many?
And then it's a cubic probably?
Sorry?
It's a cubic, the formula?
Yes.
Yeah, that makes sense.
No, I forget, actually.
Yeah. Other questions for Neil?
Yes, Neil. Yeah, very, very nice talk. What I was wondering is the relationship between this and hyperplane arrangements. I mean,
Peter Orlick.
Yes. And so, but one of the ways that when you study hyperplane arrangements, you start attaching a vector of signs to each region. So what would happen? What kind of code would you get if to each of the regions of the original, each shape, you just arbitrarily, give them a different letter, and then every region you have actually, gives you some sort of n tuple, of assignments. In other words, which region from which, you'd have to order things somehow, but this might give you some sort of code. I'm not sure how good. I don't think this code is very good code as codes go, but it might be interesting to study, what the labels for the regions.
Would that work in 2 dimensions, or would it only start working in higher dimensions?
No, I think it should work in 2 dimensions. Well, I mean, the problem is that it's not clear. I mean, in hyperplane arrangements, I mean, you have a side, so you'd have to give some arrangement. It would be a map. Well, I'm not really sure, but I was thinking it might be interesting to characterize what the individual regions look like in terms of the original shape.
Yes. Yeah. Huh? Please. Yeah. Any other questions?
I have a comment. If you were mentioned polyhedra, and if you restrict yourself to finite graphs without multiple edges, there's a beautiful theorem of Ernst Steinitz that says that those graphs, or the vertex edge graphs, are 3-dimensional convex polyhedra if and only if they're planar and 3 connected.
Yes. Yeah. Famous theorem.
Yeah. Nice talk. Thanks, Neil.
Well, thank you.
Yeah,
Nice suggestion. I hadn't thought about Steinert's.
that's a good point. More questions to Neil? Well, let's thank Neil again. And you're welcome to come next week. Thanks, Neil. And the recording will be available shortly in a couple of days. Thank you. Bye-bye.
Bye.
Bye, everyone.